The topic today is one-to-one functions and inverse function. One-to-one we see before, inverse no, inverse is new, totally new. But they are connection, no? So now I want to recall the one-to-one function and the inverse function. Now we study. And let's see 2 or 3 examples of this. Okay, let's see a function. A one-to-one, a many-to-one, and one-to-many. So for example, in the red part, this is a classical example of the one-to-one. Because any value of the x is assigned directly with the only one value of the y, one-to-one. Okay, now one husband, one wife, one-to-one. This is a function. It's obvious. Yes, it is a function because because the definition of the function, the most important is this word one. Says you have only one in the range, entonces it's a function. Otherwise, no. This is many to one. Because, for example, x1 is assigned with the y1, x2 is assigned with the x1 also. So it's obvious many to one, but it's also a function because the most important in the definition of the function is this one. However, in the green part, you see different situations. You see one to many because one y, one x1 is associated with the two different y. So when it's many here, no. Do not satisfy the condition of the function to say it. No, it is not function. A function. Okay, I suppose you remember very well this, no? The thing I want to take advantage this moment is we focus in one-to-one. Why is important one-to-one? Oh, it's important because one-to-one is reversible. Look, we see you, for example, you change the direction of the arrow. This is the function f. In opposite direction would be the inverse function. And by the way, the notation that we are using to denote inverse function is f, and you have -1 here. It can look like exponent, but actually it's no exponent. It's a symbolic way to indicate inverse function. This is equivalent to say inverse. So keep in mind that this is no exponent, this is no reciprocal, this is wrong. Okay, this symbolic way is -1, a symbol indicate inverse function. Now, when you reverse the arrow, in this case, well, no problema. It's one-to-one in both directions. So now we have the inverse. The conclusion is the inverse function. The inverse is the association in opposite direction. The inverse function exists. Okay, very, very important conclusion. And in this many to one, when you change the direction of the arrow, become like a one to many. Entonces no function. In this case, the inverse function do not exist. This is no function, so no have no sense to talk about inverse function. So now I discovered that the most important requirement to the inverse function exists is that the original function would be one-to-one. Otherwise, no. Okay. So now the next question is, one professor, how do you know que one function is one-to-one or no? Okay, it's easy. I suppose you remember very well the vertical line test. The vertical line test is using to verify if one function or one relation, no function, is a function. So the vertical line test allow me determine si it is a function. Let's see quickly. Suppose that we have one graph like that, boom, and one graph like that, boom. So now you apply the vertical, si crossing 1 point, or si crossing 2 points. This is yes, and this is no. This is vertical line test. But we have another, que es the horizontal line test. Horizontal line test. The horizontal line test allow us to determine if is one-to-one function. So suppose que the vertical line test pass. Yes, it's a function. No problem. Entonces you apply now, secondly, the horizontal line test to determine if the function is one-to-one. Because I need to investigate if this one-to-one is invertible. In other words, the inverse function exists. Okay, entonces similar. Look, let me show you. It's easy. You have, for example, a function like that. Let me see. The function like that, similar to this, or a function like that, similar to this. Let me try to do better this. The function like that. Entonces you apply vertical, horizontal, sorry. Horizontal like this, just like that. Crossing 2 points, here, cross in only 1 point. Any horizontal, no vertical. Any horizontal line que you apply, crossing 1 point. So this is a typical example. Que no, it's not one-to-one, and this yes. Let's see this apply this idea in the very, very popular function that you know in college algebra, no? Suppose in college algebra you know very well the function x squared, the QB, the reciprocal, 1 over x, the square root. Entonces now, in this case, you can apply the horizontal line test and verification si es one-to-one or no. Okay, the quadratic is, you know, the famous parabola. The cubic is something like that, the cubic function. The reciprocal is something like that. And the square root is this. Okay, this is a typical graph of the most common, you know, absolute value. Let me put absolute value. Another function that we studied. The absolute value look like that. Look, absolute value. This is absolute value. Therefore, when you apply the horizontal line test, you fail. This you pass only 1 point. You pass because crossing only 1 point. Okay, we can do you know, several horizontal. Si crossing only 1 point, pass. This pass. This no. This pass. This pass, of course. And this no. Because crossing 2 points. Okay, do you understand very well the idea for the horizontal line test?
Yes.
Now, you say, wow, professor, but it's a shame que the quadratic function have no inverse. Yeah, actually, it's a shame. Because, you know, what is the idea behind inverse function? The idea behind inverse function is like in opposite direction. And what mean, professor, opposite direction? Suppose one elementary function que es x plus 10. That is a function que you take any value and you add in 10. So the y value or the f of x, either way. And this is what would be the inverse function. So let me use the notation, the function notation. So suppose f of x, intuition. This is an intuitive idea. After I explain the scientific procedure to find the inverse function. But intuition is the inverse function is subtracting 10 because I know very, very well that the opposite, to say one word, using one word, opposite operation for the addition and subtraction, no? In the opposite direction. No? Let me try to understand. You pick one arbitrary point, x equals 5. I'm plugging in 5 here. Es obvio que es 5 plus 10, que es 15. Okay? Now suppose que I plugging in 15 in the inverse function. So that x equal 15 is a new x, que 15. I plugging in the inverse function 15, que es the x minus 10, no? 15 minus 10 is 5. Wow. And we come back again at the beginning. In other words, and this happens in any value, see you apply simultaneously in either order the composition, so together any function and its inverse. So basically any function composition is inverse is equal identity function, que is the same value. I pick 5, but you pick 3, you pick 20, you get the same result. So basically, the composition simultaneously, like a change one by one, sequentially, I apply the inverse function and the original function is equal identity function, que by the way, is equal, you apply in different order. You apply first of all, the original and after inverse. And this normally in general is not true. So when you have two arbitrary functions, no family, for example, G and F, no is equal, no F composition G. But in this particular scenario, yes, always happen. The inverse and the function, the composition give me identity. And it's a fantastic way to verification. See, the expression that we compute and the procedure I want to explain in a few minutes is true or not. Okay, so now intuitive idea is addition and subtraction are inverse functions. And why not multiplication and division? Suppose that you multiply by 2 and you divide by 2. So the inverse is divided by 2, no? Something like that. So you put together, the 2 is cancelled, and you get the identity function. And why not, professor? See, we working before with this quadratic function, que is a square power and a square root, is inverse. O sea, the quadratic, que es this, and the square root, que is this, are inverse function because you are doing both together. Suppose que the function f es x squared. Y ahí suppose que the inverse function is square root. And you pick arbitrary value, for example, x equal 2. And you plug it in the original, f4, because 2 squared 4. And when you apply the inverse function of 4, s square root 4 is 2, and we come back again. So I don't understand, they are a contradiction. You say que no es one-to-one, entonces it's impossible to talking about the inverse function. And now, yes. Okay, now the reason is that when you define the function, so 3 pieces of information that we need to define any function is domain, range, and expression. In this case, x squared. So as you define the expression alone, and you obviously delete mentally definition of the range and domain is because you suppose it's all real number. And actually, no. However, if you define a new function que is, is family of the square root, but you define only on one domain, que is only the positive number, like that. So we have a half of parabola. They have positive or they have negative, either way. But I define the positive part. Now, when you apply the horizontal line test, pass. So this is invertible. So this function, so it's important, the teacher don't explain very well this idea. It's theoretical, confusing. So to define a function, we need three pieces of information: domain, expression, and range. So now it's not equal, it's not the same function. So you see x squared, but you assume no information about domain and range, and you suppose it's a real number. Obviously, range, no. Range is bracket 0, infinity, no? Because when you square negative number becomes positive. However, I discovered that this function is not one-to-one. Okay, because it's the completely parabola, no? However, si you restricted the domain to the bracket 0, infinity, so only positive value, that the range stays the same, this new function is one-to-one, is invertible. This is the reason that some functions you need to apply some restriction in order to define the inverse function. Okay, so now some problem I say determine inverse function of the function f of x equal x squared. Entonces ponen semicolon, you write semicolon, x greater than or equal to 0. And the student asks me, Professor, what the hell is that? It's a restriction. It's a restriction in order to be one-to-one, to say it's possible in find inverse. Okay? But okay, in the example you see more clear this idea. Do you understand this? It's confusing, eh? Confusing or not?
No.
No. Okay, cool. Another thing, super important, theoretical, before I start example, is, in the sketch you see before, look, this is sketch. When you find, so in this sketch, in this, you have domain of f, and we have the range of f in that direction, so from left to right. However, so you find the inverse, the domain of the inverse is equal, bam, bam, the range of the original function, because now when you permutation, you interchange x and y like that. Now, this is my domain now of the f inverse is equal to the range of the original. Likewise, this is equal to the range of the inverse function. Do you understand very well this idea? Yes or no? Confusing?
No.
No. Okay, cool. Okay, basically you interchange x and y, therefore my old range now is my new domain. And my old domain is now my new range. It's too many words, blah, 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 but it's easy to understand, looking in one picture. Let's do an example. Example is long because include 5 steps. So I give you one function. Example number 1. I give you one function. Suppose that function is normally is the function, guys, that we study in college algebra, no? Quadratic, cubic, absolute value, reciprocal, square root. This is classical. Cubic root. Don't forget cubic root. The classical library is square, cubic, square root, cubic root, bueno, cubic, 3. Actual value is the reciprocal 1 over x. So now for each function have a corresponding domain, no? And range. Si you don't specification, entonces you suppose que es a real number, no? Okay, therefore, suppose now that we have this function, x cubic plus 3. Ooh, this belongs to the family of the cubic function. The first thing you should do, step 1, is determine if this function is one-to-one or no. Determine if f of x is one-to-one or no. Si the answer is no, entonces the conclusion is it's impossible. Continue, professor, because this function is not invertible. Si the answer is yes, well, okay. You continue step 2, 3, 4, and 5 steps to finish this. Entonces, how do you determine what is the fantastic test que allow me to determine si one function is one-to-one or not? What test? What test I need to use? Come on. Nobody know? Wow.
Is it the horizontal line test?
Horizontal line test. Entonces, I know basically the shape of this because I know very well that the cubic function alone look like that, right? And this is plus 3. Oh, entonces plus 3 is just transformation, no? What kind of transformation you see? What kind? The transformation, the fourth transformation that you know very well when you adding plus 3 or subtracting something and the y value. What kind?
Is the vertical
Vertical shift.
shift?
Yeah. Shift is
Up.
up. Very well. It's a vertical shift 3 unit up. Remember, when you adding, you don't reflecting. No. You don't deformation because when you multiply, yes, you're stretching, compressing. But when you adding 3 and the y value, the only thing you should do, what you are doing, is a motion 3 unit up. Okay, so now my new graph is similar to this, same shape, but now this point, que normally is 0, 0, now would be 0,3. Entonces, when you apply the famous horizontal line test que Anika suggest me, pass the test or fail the test?
Pass the test.
Pass the test. Okay? Entonces now you determine que yes, it is one-to-one function. Therefore, the inverse function exists. Okay. Now, what is the next step? Well, the next step is to determine the inverse function. And step 2 is determine or find. Either way, find. Find what? Find the inverse function equation. Okay. So now what should I do? Look, the procedure is always the same. You declare. So we come back at the beginning. Look, the beginning was this expression. So you replace. This is a function notation, f of x. No f of x anymore. I replace by y equal x cubed plus 3. You know that they are equivalent, no? Y and f of x is the same. Of course, f of x give me some advantage to understand transformation, to understand in a set, x in a set, y in a set. This is the countable way to express the same idea. Now, this is the most important moment. Now it's the most important moment. To find the inverse function, you interchange x and y. This is the most important moment. So now I copy x equal y cubed plus 3. Do you understand the thing I am doing? Do you understand the thing I am doing? Okay, now voila. This is the inverse. But the inverse is no good or no nice. Okay, let me copy this idea here. Because this is the inverse expressed in implicit form. Okay, so implicit means que y is not isolated, pero I need explicit form. Explicit is nice. Explicit is when the y is isolated. Okay, let's do it algebra. In this case, it's easy. Okay, no. But in this case, yes. You isolate the y. How? You subtracting 3. You apply cubic root both sides. Now cubic root x minus 3 equal y new. And this y new is the inverse function. The fantastic conclusion is then the inverse function expressed in function notation is a cubic root x minus 3. Boom. I finish the step 2. You understand very well or no? We are doing in this order. So another function that we studied in this chapter. Yeah, I need to find the inverse function. Now you interchange x and y and isolate the y in order to express in explicit form. And this makes sense or no? Use intuition. Compare, please. Compare this. Get the original and this. Get the new one. Okay, obtain. As the inverse function, remember the intuition of the inverse is opposite direction, is opposite operations. And the original, according to the order of operation, we are doing the cubic power first. And after plus 3. In this case, you subtracting 3 and find a cubic root. Okay, cubic root and cubic power, you know, is inverse function. Does it make sense? You see or no?
Yes.
However, the fantastic way to verification is no intuition. No, it's doing strictly by the composition. So you put together F composition, F inverse, And why not f inversa composition f, and magically you get the same value as the identity function. Because on those each other, that's the interpretation, on those each other. Let's do it in this order. Let's do it in this order. I suppose that the first function is inverse, que es this. Okay, so I put this, totally this, inside here. Composition. So basically is, you copy big parentheses, you replace x for this expression que es cubic root x minus 3, cubic plus 3. Do you understand the thing I am doing? You take the inverse. Remember, the composition have a specific order. The function que es, you know, is in the left part, is the first function that you need to apply. So you take the inverse functions at the inverse function, and you replace this inverse function into the x of the original function, and you are doing composition, right? So you are doing an opposite direction. Well, in opposite direction is different. Opposite direction, you take this, okay, and you replace here an x. So the thing I am doing now is cubic root x cubic, no x is x cubic plus 3 minus 3, like that. Do you understand the thing I am doing? Oh no, it's confusing, no? Answer me, please. Oh, yes, it is. Okay, Apolinario. Okay, Apolinario, look at that. The cubic power and cubic root cancel out. You know very well. And we have x minus 3 plus 3. Wow. 3 and minus 3 is 0. And we get identity function. Just need more example. Emily, just need more example. Okay. But the important is, I prove this. Okay, when you put together the inverse function and the original function, the answer is identity. Okay. In this case, similar situation happened. This 3 is cancelled. And we have cubic root of x cubic is again identity function. You see that? Okay, this is step 3. Step 4, in this example, is determine domain and range. But domain and range of what? Of both. O sea, for the original function f and the inverse function, determine domain of f, range of f, domain of f inverse, and range of f inverse. Bueno, es obvio que cubic root, this es obvio que the original function, que es like that, x cubed plus 3, the domain is all real number. And the range is all real number. Only look in the graph, you can see it's clear. However, remember, domain of the original is equal the range of the inverse. It's a coincidence. No coincidence. This is a fact. And this is the same. Like the coincidence is everything is equal in this case. This is a step number 5. Now step number 5, que is the most important step, is do the graph. Do the graph. So a graph. Graph who? Both f and f inverse. And you see it's extremely easy. I want, of course, we are doing decimals, no? However, I want to do at least one example by hand, no? Let me try. Let me try to find the rectangular coordinate system. Maybe this folder. Yeah, wow, beautiful. There you go. I like this. Look, let's doing the graphic of both of the function f and the function inverse. Remember, the function f is given at the beginning is x cubed plus 3. Okay, so I need at least 3 points. The famous point 0, 0,3 is the y and z, because when you suppose get x is 0, 0 cubed plus 3 is 3. Therefore, the point is 0,3. This is the x value, and this is the y value. I need 2 more points. Suppose I need in 1. Try to take arbitrary easy. No 100, no 50. 1 is good. Entonces 1 cubed plus 3 is 4. And the point is the point 1,4 plus that 1,4 and negative 1. We always using 0, 1 and negative 1. Entonces negative 1 is cubed plus 3 is 2, because negative 1 cubed is negative 1. And negative 1 plus 3 is 2, and the point is the point negative 1,2. Negative 1,2 would be here. Negative 1,2. And makes sense because the graph look like that. Look, let me show you. Approximately, you know. This is the graph of the original x cubed plus 3. And to do the graph of this, we can use a transformation. So we compute that the inverse function is cubic root x minus 3, no? It's inverse function. We can plot, you evaluate in different points, but no, much better using the idea for the interchange x and y. Look, interchange x and y. Therefore, point by point, suppose that point is 0,3 would be 3,0. 3,0. Because the only thing I did was interchange x and y. This point is 1,4 would be 4,1 here. 4,1. This is fantastic, guys. And this point is 2,1 is negative 1,2. Sorry, is 2, negative 1. And the graph of the inverse function look like that approximately. You know, this is the graph of the cubic root x minus 3. And by the way, it's no coincidence, it's a fact that these graphs are symmetric with respect the line y equal x, que is identity function. Suppose here I write identity function 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, negative 1, negative 1, negative 2, negative 2, and you are doing a line like that. Bam, 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 bam. This is a line that corresponds with the identity function y equal x, and this is symmetric. Symmetry means that the distance is the same distance always here. Symmetric. Do you see the effect? Always.
Yes.
100% happen. Just in case, I want to show you in this more clear this example. Remember, always when you need to do a complicated graph, nobody doing in the piece of paper. No. Everyone doing in Desmos. Okay, there you go. Do you see Desmos now?
Yes.
Okay, just look at example 1. It was y equal x cubed plus 3. I copy the identity function. I copy the cubic root. In this case, I using fraction exponent is equivalent, you know, but the problem is in decimal we have no cubic root. Okay, now look, bang, bang. Okay. In black color, I put the. Let me change the color because I using red color, no, and the board and the white board. And the inverse function I use in blue color. I change the color. Okay, cool. Now it's more clear. And the typical point 0,3 and when you interchange x and y 3,0. Wow, look at the symmetric with respect to the line y equal x. Another point is 1,4. I understand a lot better now. Wow, thank you. Okay, was okay. I understand better now. It's Anika. Anika is very dynamic. O sea, cuando está something exciting. Choo, I got it. Okay, so this is the first example. Super easy, super straightforward. No, I don't want to complicate too much this. I want to see another more example, and in the review packet we see more. In the review packet we see more of this. Okay, let me come back to the whiteboard again to analyze the second example I bring for you. Okay, whiteboard. You see my whiteboard?
No.
No? Wow. Okay. Yes, Anika is a yes. Everyone saw or no? Not yet, because sometimes I have some delay, no? See, no, I try to fix it. Did you see whiteboard or no?
No.
Not yet. Okay, so I stop sharing. I suppose in this moment you see my face. No, it's a Bernardo is a no. Now I share Microsoft Whiteboard. Yeah, I open that. Now?
Yes.
Okay, cool. Now, example 2 is super easy. I don't want to complicate your life because we have too many things important to study. Example 2 is about another function. Wow, f of x equal x squared semicolon x greater than or equal to 0. Wow, what the hell is that? Well, when you see that, it's because in the problem you have restriction. So this is actually my domain. Okay, this is actually my domain. So no, it's not free que you suppose que es a real number. No. We have one que is a positive and includes 0. So in the famous interval notation, this is equivalent to say bracket 0, infinity, no? It's equivalent. It's the same thing. Okay, so now step 1. Do you remember step 1? What is the step 1? I don't remember. Step 1 is determine what? What is the step 1? Please help me. Come on, answer me.
Define the one-to-one.
Exactly. How? Emily, no? Emily. Who is speaking? Emily. Because I see Emily, yeah. Determines if one-to-one. How you find si es one-to-one or not? What are the tools that we are using? Come on. Horizontal test. Horizontal line. And what do you think? Pass or fail? Well, I know very, very well. Okay, this is the quadratic function, no? And the quadratic function, yeah, fail. The quadratic function is like that. However, according to this restriction, this is x squared without specification domain, because default you suppose que es all real number, but in this case, no. My function, guys, is important. This is very, very confusing. I understand very well. To define a function, not only you define the expression. This is one piece. You need to specification, domain, and range. 3 pieces we need. The problem is in the majority of the example, we omit frequently this idea. But this is important. See, now my domain is only the positive part. Es obvio que that part disappears. So my parabola is a half of parabola, right? This is the same expression, but different domain. This is bracket 0, infinity. Okay, and this new scenario, what do you think? Pass or fail?
Pass.
Exactly. Pass because when you apply the famous horizontal crossing 1 point, here no, fail. Okay, but forget about because my problem, so do you understand now what is the reason que in the problem, so in some problem, not in all of the problem, but in some problem, specification after the semicolon, the restriction, que es the new domain. Okay, so now, si es one-to-one, so we can affirm, yes, it is one-to-one. Therefore, it's invertible, que es equivalent to say, synonymous to say, the inverse function exists of this function, only this supposition, and this no. Okay. Okay, now ready. Step 1 was analyze si es o no one-to-one. Therefore, si the answer is yes, we move on to the step 2. And the step 2 is determine or find the equation for the inverse function. And it's predictable because the inverse function for the square power is the square root. But okay, let's do it in the traditional way. F of x is equal x squared. You replace for y because it's more comfortable in this way, and you interchange x and y. Now you have x equal y squared. Okay, cool. This is inverse and implicit, but I need explicit. And explicit, you find the square root because I need to isolate the y. Entonces, square root x is equal y. And this is the new y, que es inverse function. In conclusion, the inverse function is the square root. Exactly we predict. You know very well. But professor, I don't understand something because normally when you apply a square root, you put plus and minus. And the reason is no, only plus. Remember the restriction. We're using only the positive value, no negative value. Okay? Remember, because square root negative number is imaginary, no? So it's completely out the domain. This is the reason, confirmation that we are doing well. Step 3, que es the last is the graphic, well, domain and range. The step 3 is forming the composition. The composition is you put together that function in this order. Entonces now the inverse function is this, que es square root. Inside you put x squared, que es the original. The original inside here. And together give me identity. Because I know very well that square root and square power cancel out each other. Now, in this scenario, we have a square root x squared. It's the same. Do you see? And domain is easy. Look, domain and range of the original function gets given at the beginning, square power, is, bueno, es this domain que es given. Entonces, no, you can, normally, in our class before, you assume que es a real number. No, pero si es a real number, no, it's not one-to-one. Entonces, the restriction was this, bracket 0, infinity. Es obvio que the range is exactly the same, because any number doesn't matter. It's positive. Do not accept negative number to be one-to-one. The square root, the positive number is positive. O 0, que es 0 es especial. And the square root, que es the inverse function. This is the original, and this is the inverse. Domain and range is, you know, the domain is the range of this, and the range of this is the domain of this. And this example we are doing it, there are coincidences, everything is the same, but not necessary. There are another example that are not necessary. And the graph, let's do it in this one. Bueno, it's the same idea. You plot 3 points, and don't forget the symmetry with respect to the line y-x, and that's it. Let me try to do in Desmos to see more elegant. Okay. Desmos. Do you see Desmos? Do you see?
Yes.
Example 2. Okay, example 2 is a function x squared. Look, look at that. X squared is the function blue. Okay, and 3 point in the positive part, of course, because remember the restriction. And the positive part, we have the 0,0 because 0 squared is 0, no? And 1,1 is a coincidence because 1 squared is 1. But 2 squared 4. We have 3 points. And likewise, when you interchange x and y, the point 2,4 become 4,2 in the square root function. 1,1 stays the same. It's a common point, and 0, 0 is a common point. And the identity function bang is totally symmetric line, symmetry line. Cool? Do you understand very well or no? Yes or no?
Yes.
Cool. Let me come back to the whiteboard. Guys, I want to start the complicated part. Not complicated, but the new part. The new part is the, okay. We studied in this chapter 2 new functions that you never see before, with me at least, no? Maybe in the high school you see, or you remember, or you don't remember. This is like a transcendental. Transcendental is because transcend beyond the other function that you know. You said the other function that you study is the polynomial, maybe, and rational. So this is a new. It's no polynomial, it's no rational. It's called transcendental function. And we studied 2 here in this subject, but in trigonometry we study more transcendental, que es the trigonometric. Okay, entonces the first function que we study transcendental is this exponential function. Exponential. Okay. Actually, it's not one, it's a family, no? Entonces es exponential function en plural. That's what definition. Definition is you have function f of x is equal a to the x power. So the independent variable x is now located in the exponent. It's important that you understand the differences. Suppose a is the base. A is the base. Suppose one elementary example. Suppose que the base is 2. Entonces, the function is 2 to the x power. Okay, this is completely different, guys, to the x squared we studied before. This is quadratic function because the exponent is constant 2 and the base no. The base is variable. This is completely different. The exponent is the independent variable x is located in the exponent part and the base is constant. Okay, this is exponential when the exponent is variable. Entonces this is exponential. We have two kinds. O sea, the restriction for the base is no arbitrary value. In general, is a real number. And that means real number is fraction, irrational, crazy, pi, radical 2. But important, the base is always positive, never negative. It's totally out the definition. Base negative. No, have no sense. It's not exponential. It's another weird thing. The base is maybe 2, maybe 3, maybe 1/2 positive. But we have two limitations. It's no 0 and no 1. Why? Because it's a trivial example. Because 0 to the any number is always 0. And 1 to the any number is 1. So this is stupid. Trivial example. Now exponential is, for example, real number, pero positive. So negative base is totally illegal. It's no definition. It's out definition. It's no exponential. It's another thing that have no name because it's crazy. Entonces, for example, you have 2 to the x, okay. 3 to the x, okay. 4 to the x, okay. Radical 2 to the x, okay. Exponential function. Pi to the x, okay. It doesn't matter que it's rational, irrational. And what about fractions? For example, 1/2 raised to the x, yes. It's also exponential. The only important thing is that the base is positive number, real positive number. 3/4 raised to the x is also exponential. Okay. However, I want to take advantage of this moment and differentiate two kinds of exponential. Okay, it's also exponential, but two kinds. Two kinds. You have, for example, if the base, que es a, I call a the base, is greater than 1, this exponential is increasing exponential. Sometimes it's called exponential growth. Exponential growth. Okay, because the function you see after that, the graphic is increasing. Boom, it's going up. However, another possibility is that the base is fraction, so less than 1. So actually it's in between 0 and 1. Remember, 0 and 1 are illegal. Okay, and this is decreasing exponential. And both are important, guys. And this is exponential decay. Exponential decay. And exponential decay is the decreasing function like that. 1. 6. Okay, so basically, let me try. This is the all real number line. This is all real number line. The legal value of the definition for the exponential is, look, this is from negative infinity, positive infinity, negative infinity. The important point, 0 here in the middle, 1, okay. We have exponential only here, in that part. No 0, no 1, and this is decay. This is decay, here decay. And we continue here, exponential on the base. This is the base value, Okay, this is growth, exponential. Okay, 0 and 1, no, trivial, and negative, illegal. Of course, no. Only in the red part. Let me highlight this. That part and that part. And you need to differentiate. Okay, when the base is less than 1 is decay, and when the base is greater than 1 is growth, exponential. Let's see one couple of the example confusing before I start the property in detail. Suppose in the test I give you this example, 3/2 raised to the x. And 2/3 raised to the x. Y equal this, and y equal this. My question is, this is exponential, yes or no? And this is decay or growth, exponential. This is question 1, and this is question 2. What do you think? Opinion. Opinion. A ver, Sofía. Yamin. Destiny. Apolinario. Yami. Elsa. Anika, que always Anika participate. Emily, que always like. And Karen, are you quiet? Karen, are you are in the campus right now? Karen. What happened, guy? Anika left. Anika joined. Okay, there's no idea. Nobody have idea what is it? Is exponential or no? Number 1 question.
Yes.
Yes. Both?
Yes, I think so.
Yeah. Remember, the only restriction is that the base is non-negative. If it's positive, it's okay. And what is growth or what is decay? 3/2 is greater than 1?
Yes.
Yeah, entonces es growth. And 2/3 is less than 1, ¿no? You put in the calculator, ¿no?
Yes.
This, yeah. Exactly. This is 1.5 in decimal. You put in the calculator, no? And this is 0.6 repeated. So this is growth. And this is decay. End the story. Do you understand very well or no? Confusing?
No.
No. Okay.
No, it's very easy.
Now, let me try to study in detail the exponential function. So I take one example, no? Example 1, I want to study the property of the f of x equal to the x, in which the base is 2. Let's see what happens when the base is 3, 4, 5, 6, 7. No? It's easy. And it's a classical in the test. I ask you, do the graph of the exponential. Okay, so for example, suppose I want to do the graph of the exponential. I create one table. So let's do it by hand. This is the x value. Entonces I put all real numbers 0, 1, 2, -1. I put 3, 4, 5, but no, -1, -2. It's enough. 1, 2, 3, 4, and 5 value. And here is y equal to do the x. And here I put x comma y, que es the point I plot on the rectangular coordinate system. So now 0, 0, x equals 0, y would be 2 to the 0. I need to know that any number or expression raised to the 0 power is always equal 1. Now the point is the point 0, 1. Wow, wow, wow. Then, professor, this point is universal. Universal point, any exponential passing through the point 0, 1. Because regardless, what is the base, que es 2, 3, 4, 1/2, either. The answer is always 1. Now this is a universal point. Remember, when I'm doing the graph of the any exponential, don't forget 0, 1, universal point. Okay, now y is equal to the 1, because I suppose now that x is equal to 1, it's obvious que es 2, and the point is 1, 2. Cool. Entonces now, when the x is 1, the y value is exactly coincident with the base, que es 2. Because it's, si es 2, es 2 to the 1 power. Si es 3, es 3 to the 1 power, es 3. Entonces it's 2 is because it's coincident with the base. This is a typical point. Typical nice point. 2 is y equal to the second power, is 4. And the point is 2,4. Okay, now -1. Y is equal to raised to the -1. So I need to remember what means negative exponent. It's reciprocal, 1/2, right? Reciprocal, entonces 1/2. And the point is -1, 1/2. This is another typical point. In which if you evaluate the exponential at -1, we obtain the reciprocal of the base, 1/2. Entonces, this point, and this point is enough, 3 points, to plot the exponential. You want more? It's okay. Now -2, well, -2 is y equal 2 to the -2. Oh, negative exponent one more time is reciprocal. A reciprocal of what? Of the 1/2 squared. So 2 to the -2 is equal 1/2 to the second power, and to the second power 4 is 1/4. It's 1/4, 1/4. Entonces it's -2, 1/4. It's another point. You have 5 points, enough to visualize the graph of the exponential. Let me try to do my best by hand and after in Desmos. Okay. Let me try. Here. Oh, I have the rectangular coordinate system in the piece of paper. Let me enlarge a little bit to see. Oh, I plot the famous universal point. Is this 0, 1. It's super important. 0, universal. I plot 1,2. 1,2. Here. 1,2. 1,2. I plot another que es 2,4. Oh, 2,4. Okay, 2,4. Curiosity. 3 would be 8, no? Because 2 to the third power is 8. And 2 to the fourth power is 16. Wow. And 2 to the fifth power is 32. You see que exponential is a function increasing faster. So when you hear this increasing exponential, it's because increasing faster. So you compare exponential versus a square, this wind increasing faster. than this both increasing, but this increasing faster. Okay, and si the base is not 2, it's 3, it's faster. Okay, okay, enough. Entonces now, increasing faster like that. Okay, now what about the negative part? Oh, I forgot the negative part. This increasing faster in the positive direction. Wow. However, in the negative direction, well, it's increasing, but it's a small increasing, no, it's slow, no increasing faster, no. And negative 1 is 1/2. Remember, it's 1/2. And 1/2 in this segment, let me make a zoom to visualize more clear that part, is this point. Boom. This point is the point, negative 1,5. Okay. And now negative 2 is 1/4. It's a half of the half. I suppose que here it's a negative 2,1/4. And so on. And so on. Entonces, this increasing, it's increasing because remember, the analysis of the increasing or decreasing is you walking from left to right in the x-axis. Never you go back, like a Michael Jackson. No, Michael Jackson. You go from left to right. Entonces, I am doing in opposite direction. Entonces now you can see, you can see que the curve of the exponential approach it to the x-axis, but never touch. This is asymptotically. So we have here one horizontal asymptote at y equals 0. Any exponential function. This is very, very important piece of information when you are doing the graph of the exponential. Contain one horizontal asymptote at y equals 0 que es coincident 100% with the x-axis. Okay? So what is the most important property, professor, que we study here? The most important properties of the exponential is number 1, domain. What is the domain? Domain is already a number. We have no restriction. We have the exponential function completely to the left and to the right. Right to positive infinity, negative infinity. There are no restriction. It's nice function, never to be undefined. But the range, no. The second property is the range is you see only positive number. We have no exponential in that part negative. No. Never. The answer for the exponential, give me negative number. You see in the equations, okay, sometimes, for example, some people say this equation, 2x equal -4. This is impossible because the exponential always offer positive number. This is a contradiction. This is no solution, this equation, suppose. Keep in mind this. The range is only from 0 to infinity positive, so the positive part, but not include 0, because it's asymptotically, actually never touch this. The function is increasing, the behavior, number 3, behavior is increasing function. Okay, increasing function. Remember the idea behind the increasing. You travel on the curve, and this is the roller coaster car, and travel always from left to right, and I see that the roller coaster car go up, that is increasing, and as a confirmation that this is the growth exponential. And the reason que es growth exponential is because the base que I select in this example was 2, no? The base A is 2. And si es 3, si es 4, es also greater than 1, entonces increase. Okay. The function is neither no symmetry, no even nor odd, and neither. So we cannot take advantage the symmetry, and also is one-to-one, one-to-one. Because when you apply the famous horizontal line test pass, you know, to say I predict in the future okay, we have inverse function. And the inverse function I anticipate of the exponential is the logarithmic function. And let's see the complication behind this. But I anticipate something. And number 5, extremely important property, that we have horizontal asymptote at y equals 0. Don't forget that. When you are doing the graph, I need to see the graph. I need to see in dotted line, the horizontals. And the typical, this is the most important moment now. 6th property. The typical, what is the typical points que you never forgot? Bueno, the universal, que es 0,1, don't forget that. And 1,2 and negative 1,1/2. Bueno, in this example, because the base is 2, pero si the base is not 2, suppose que the base is 3 or 4, let me try 4. Because in the test, I asked you do the graph of the any exponential, no? I suppose que in the test, I put exponential f of x equal 4 to the x. Do the graph of this. We are doing in 2 seconds. In 2 seconds, how? Well, it's similar to this, except very, very similar to this. You plot the universal point, que es 0,1. Sorry. Let me try to make it zoom and compares both. 0,1. This is universal, guys. This is the point. Any exponential passing through this is family. So you can interpretation the family of the exponential is like that family. Depending on the base, you know, and the negative bar is similar. But in this specific, the typical point are 0,1, nice. 1,4, because the basis for 1,4 is here. 1,4 and negative 1,1/4, reciprocal. Okay, so now it's a little bit hard to see 1/4, but it's a half of the half. So it's half of the half, I suppose, here. And you are doing approximately the graph of our exponential, okay, in this case is 4 to the x power. And don't forget, please, the asymptote, que es at at y equals 0. It's a horizontal asymptote. And don't, I did the graph in 5 seconds. The graph, 3 point, depends on the base. I know que es exponential growth because the base is 4 greater than 1. And that's it. End the story. Cool?
Yes.
Okay. Now, let's see what happens if the base is no greater than 1. Suppose que in the second example, that was a complementary example. Look, I put 4. And the second example, official second example, we are doing the graph of the exponential. So example 2, f of x equal 1/2 raised to the x power. Ooh, what is the complication now? When I put the base less than 1. The professor explained me que when the base is less than 1 is exponential decay. But I need to verification this. Okay, decay is synonymous to say decreasing. So let's do in the table again. Similar table to the table that we are doing before. X is 0, -1, -2. No, 1, 2, 3. Hello, positive first. Positive first. Now -1 and -2. And now it's y equal 1/2 x. And this is the point x, y. Oh, I know que 0 is universal. It's 0, 1. Nice. Because 1/2 raised to the 0 power is 1. Any number. It doesn't matter que es fraction or decimal or whatever. Raised to the 0 power is 1. However, n1 is 1/2 raised to the 1 power, que es obvio que 1/2. Entonces 1, 1/2. And 2 is 1/2 raised to the second power, que you know, using the property of the exponent 1/2 raised to the second power is equivalent to say 1 squared and 2 squared. 1 squared is 1 and 2 squared is 4. It's 1 over 4. And the point is 2, 1 over 4. And -1, -1 is complicated because negative exponent is reciprocal. Suppose -1, you have -1/2, so 1/2 raised to the -1. You flip it that. It's 2 over 1 raised to the 1 power. It's just 2. It's 2. Entonces es -1, 2, que es the reciprocal of 1/2. So negative exponent, this is a new thing. It is important that you organize in your brain. When you raise exponential, negative exponent is reciprocal. And -2 is similar, is 1/2 raised to the -2 power. If flip it, it's 2 over 1 raised to the second power, and it's a 4, no? 2 to the second is 4, and 1 to the second is 1. It's 4. Y equal 1/2 raised to the -2 is 4. And the point is -2, 4. Okay, let's do it. Let's do in the exponential decay and interpretation of this. Interpretation of this. Okay, look at that. Look at that. Look at that. Okay, I plot the first point, que is universal. 0,1, this guy. I plot this typical, I plot this typical. 1,2, 1,2, 1,2. I suppose que here. Half is, you know, in this segment is a half. This point is a point, 1,1/2. And this one is -1,2, -1,2, here. -1,2. Wow, entonces now the exponential look like different. Look like that. And this is go in that direction, and this go in that direction. One more time happen. We have here the horizontal asymptote. Remember that curve. Approach but never touch this horizontal asymptote at y0. You see it's decreasing because when you travel on the curve from left to right, the roller coaster car go down. It's decreasing. It's decay. Clear? Clear?
Yes.
And remember in the test, I put another example, not necessarily 1/2. Suppose I put 1/5 raised to the x power. How we're doing the graph for this? Okay, easy. 2 seconds. Okay, I spend more time try to find the rectangular coordinate system in accommodation que to do this. Because I plot the universal point, que is 0,1, bam. So this graph half that point. Entonces, and 1 is 1/5. And 1/5, I don't know si it's like that here. You divide this segment in 5 portions and you take the first one. And -1 is reciprocal que 5. Boom. We have 3 points. I do the graph. Do you follow me? And don't forget, please, the horizontal axis. Okay. Okay, let me try to summarize the information in decimals. Now, I suppose it's enough for today. Let me try. And decimals, I need to find another script. Get the exponential script. Okay, now let me try to share with you the decimals. Okay, do you see decimals? Oh, not yet. Do you see?
Yes.
Okay. Okay, entonces now I want to show you exponential base 2, que es exponential growth. Ooh, look at that. I plot a lot of points. I plot the universal 0,1, 1,2, 2,4, 3,8. Wow, it's enough in the positive part. And the negative part is negative 1.5, que es 1/2. Negative 2 is 1/4, que es 0.25, and so on. And you see the curve, this is the exponential, guys. Look, exponential curve, exponential growth, increase. And we have the asymptote, n0. This is important, so if you forgot the asymptote, it's incomplete the answer. Okay? This is part of the game. Now, suppose exponential decay, suppose 1/2. Oh, 1/2, the base is 1/2 now. So I predict que es exponential decay. Boom, look at that. Look at that. And make sense. Yes. I want to explain why when I come back. But let me finish this. We have, again, the same point, universal point 0,1. But in the positive direction, 1 positive is 1/2, and 2 is 1/4, and 3 is 1/8. Decimal is 0.125. You know, and decimals, no fraction is decimal approximation. And the negative part is -1 is 2, because 2 is the reciprocal of the 1/2. And -2 is a reciprocal of 2, pero square, is 4. Do you see that? This is exponential decay. Look, decay. Cool? Okay, one more thing. One more thing. I need to explain. Let me try to share the whiteboard. One interpretation. You see whiteboard?
Yes.
Okay. Okay, one interpretation of the, you know, the differences. Look. Okay, we have, again, the famous two examples. The exponential y equal to each. The exponential y equal, black color. The exponential y equal 2 to the x, and the exponential y equal half to the x. I see clear that this is exponential growth, universal point, two typical point is 2 and 1/2, is something like that. This is 2 to the x, and another is 1/2, que is similar except case in opposite direction. Wow, why? This is 1/2 raised to the x power. Oh, the reason is because one way to see that is, I know very, very well that 1/2 is 2 to the minus 1. Reciprocal, right? So you, for example, you replace here, we have 2 to the minus 1 raised to the x. Oh, and you remember the property for the exponent, and the exponent in different level multiply each other. This is 2 to the minus x. Wow, compare this expression and this expression. Wow, this expression is the same, but you replace x for negative x, classical reflection. When you are doing this action, when you replace x for negative x, reflection. And you see clear, reflection will respect the y-axis. This curve, when you're reflecting, is this curve. Clear? Clear or confusing?
Clear.
Clear. Wednesday, entonces we continue with the exponential. We continue with the equations. Apollinaris is clear. Okay, guys, entonces now try to start doing the homework. Okay, this is a little bit complicated, this chapter. I don't know. I hear some students say, no, I never understand this. Okay. You try to understand because it's important. Okay. Entonces, that's it for today. I wish you have a nice day. Bye-bye, guys.